So, friends, what does, I call you friends, I hope we all agree on this. What does it mean for something to be organic?
More complicated.
More complicated.
Natural. Pure.
Natural, pure?
Original.
Okay, Hannah is in the ballpark. Carbon-based is what we mean when we say organic. Now, that causes me grand confusion when people talk about organically grown foods. I remember as a kid, people were talking about organically grown. I'm like, well, that means it's, living as opposed to non-living grown. I don't know. And so the organically grown food means something different than organic chemistry, and I'm not sure what it actually means. And frankly, I don't care that much. So studying organic chemistry, there are over 13 million organic compounds known to man. Now, if you want to be specific, there actually is a more exact definition of organic. Since I've taught origins a number of times, this is something that comes up. Organic compounds are the compounds that are used in living materials, which are pretty much carbon-based compounds. And so we have, amino acids, things that we will see a very small amount of. He is on fire, en fuego, right? Yeah, and excited too. Okay, so they used to believe that these compounds could not be created except in living things. So basically, the organic compounds could only be made by living things. So you couldn't have, I mix this chemical and that chemical and produce an organic compound. And so the actual big breakthrough, and I think it was in the 1800s, was in finding a way to synthesize urea, which, as you might guess by the sound, has something to do with what's in your urine. And also, I think, with gout. So they were able to synthesize urea and say, hey, here's an organic compound that we created without it having to have a living thing creating it. And then further research has gone on down the road. You guys ever heard of the Miller-Urey experiment? No relationship to urea. Oh, hey, look, it's a box. Anyone heard of the Miller-Urey experiment? No? Well, it's a really important experiment in the debate of evolution and creation. Miller-Urey, oh my goodness, you can't see anything. No one has said a word.
Well, it was just talking about
You're like, I wonder why he's not showing us any slides today. Oh, man. Well, it'll come up here in a few moments. I feel like a genius. Yes, so Miller-Urey, they did an experiment to try to simulate how the amino acids, the things that comprise pretty much everything in our bodies, the things that proteins are made of, how those could occur if there is no God. Right? If there's a God, it's not a problem. God can make it, right? But if there's no God there, how could these things occur? And, it couldn't be made by other people if you're talking about how did life evolve. And so what they did is they made themselves a chamber, and in that chamber, they put a bunch of chemicals that they thought would be present in the Earth's waters and atmosphere in the early days of the Earth. And then they put in things to give it energy, because you've learned to make chemical reactions go, you often have to put in some activation energy. And so they had one place where they heated it. They had another place where they had wires to make electrical arcs. And then they just let it sit there and brew for a while. And then they checked out what they had, and they found that they had created virtually every amino acid that we need for life, plus a lot more that are not included in life. And so that was hailed as a big advance to say, yes, evolution could occur because we could have just natural processes make these organic compounds that are necessary for life. Now, there's a lot more that goes into this. There are, creationists saying, well, there's really some big problems here. Number one is that you have the wrong atmosphere, and it goes through. So you have debate, and pretty much creationists will poke holes in it, and evolutionists will say, that doesn't matter. That's not a big deal. But now we understand that you didn't see that square. You never did. That we can synthesize organic compounds without life. So we can have synthetic organic compounds. So for instance, you can have synthetic testosterone, which, epinephrine, right? Is, I think, synthetic testosterone. It's not created in an animal, it's created in the lab. And they find about 100,000 new organic chemicals every year. So they're learning a lot. Natural, what they used to think they all came from. Synthetic is man-made, where we have synthesized it by mixing chemicals in the right environment, putting in a catalyst, maybe putting in an energy source. So what's so special about this? The key thing about organic chemistry is the carbon atom, which connects with strong covalent bonds. So a picture, believe me, the textbook thought the picture is worth a billion words here. They had, 150 some slides for this chapter that I narrowed down, obviously, quite a bit. So here's just some compounds showing the strength of a single carbon bond versus the strength of a single nitrogen, strength of a single oxygen, and strength of a single sulfur bond. The carbon bonds are the strongest there. Something else I want to make sure that you understand looking at this picture. Are those complete molecules shown? No, there you go. No. The carbons. How many bonds should a carbon form? 6. Okay. This is an important thing. If we look at carbon back there, you have the first column, lithium, right? Has 1 electron, it's valence. Beryllium has 2. Boron has 3. Carbon has 4. So how many covalent bonds could it possibly form? 4. And so 4 is what it's going to form unless you have some special thing. There are special things that occur, but we're not looking at those. So it should have 4 bonds. So if you look for the instance of the 2 carbons on the top, it only shows 1 bond for each of those. Something's missing. Here's a little chemistry trick. If you don't see it, you assume it's hydrogen. And so, since we have only 1 bond of the carbon, we would just assume there's 3 hydrogens on it. It's kind of annoying to make that assumption. But as you'll see in a moment, we make stick figures where we assume the carbons as well. If you see a bend, assume it's a carbon. It's another rule. So you would have three hydrogens on that one. How many hydrogens do I need on the one below it?
2.
I need 2 because it has 2 bonds already. How many do I need on the center one? None. Yay, that one was right. And then we could go on, we could put the other hydrogen on. I'm not going to, but that's something when you're looking at these chemical structures, you say you look them up on Wikipedia. You're going to see things on Wikipedia that don't show any atoms. They'll just show something like this. And you'd be like, I don't know. It's a big nut. I don't know if you guys watch Robot Wars, but that's their trophy, is the big nut. What this means is you have 6 places where it bends. And so based on our abbreviated drawings, what does it mean to have a bend? A carbon. And so there's a carbon at each one of those red dots. And this circle in here actually is a shortcut for saying that you have double bonds going between every other carbon. But because that is absolutely indistinguishable from this, right? I just changed which one had the double bonds. That circle represents that it's a hybrid between the two. Like we would say maybe 1.5 bonds for each one because it's shifting back and forth and the bonds are very fluid. And so we have 1.5 bonds for each of these, and then we have hydrogens to add on to make it so we have the right number of bonds. So if you have 1.5 for each of those lines, then that's a total of 3. So how many more bonds do you need? If you have 3 bonds in each hydrogen, how many more do I need? A total of 4. So if I have 3 and I need 4, I need 1. There, very good. So that means that there's 1 hydrogen attached to each one of those red carbons. Right? That's a shorthand so that you can look at these chemical symbols and understand them. The whole goal of this slide was none of that shorthand, but I wanted to point it out so you don't get confused. This kind of molecule doesn't occur. That's a chain of sulfurs. You're not going to find that. But you do find that with carbon. You'll find chains of carbon that form loops like the one I showed with 6 in it. I left this in for reasons God only knows. The book had this figure for diamond that has those carbons in a grid. And that's so not what diamond is. Diamond is pure carbon, no doubt. But the diamond structure is one of the most annoyingly complex structures I had to deal with when I was taking crystallography class. So I have down here in the corner, that's the repeating unit in the diamond structure. You can see that repeating unit is pretty complicated, and it's not just a little square grid. So the textbook's picture was really misleading. But carbon is the entire thing of diamond. Now, since I'm on this reminds me of things. The homework. Question 3 on the homework, if I would have looked at the textbook's answer, I wouldn't have decided, because the textbook's answer was indefensibly wrong. It asked about what causes a covalent bond to form. And it gave you 2 options, either the need to complete the outer shell or the, the charge of the nucleus. And it said the charge of the nucleus, which makes no sense, none at all. And so in my explanation, I explained the bonds are formed because it's lowering the potential energy state. And so everything is to lower potential energy state. And as we talked about at the very beginning, the elements have a lower potential energy state if you have a completed shell. And so in the covalent bonds, you're sharing electrons, so both atoms can say, hey, I got 1 more, I'm closer to completing the shell, and it's a lower energy state. Now you notice I said the atoms say, and the atoms want. That's what we call anthropomorphizing. We're taking something that's not living and treating it as if it has living aspects. Everybody knows the atoms don't think. And yet the textbook says, and furthermore, we need to be careful to not say that the atoms need a completed outer shell because they're inanimate. Well, that was asinine. It doesn't matter that you anthropomorphize them or not. Nobody thinks that they're living, I hope. Okay, so that one there, we'll be generous in the grading there, but the answer to the textbook was just wrong. I went and double checked with Ken Osborne just to make sure, I as a physicist am not looking at this differently, and he's like, oh, no way, the other answer makes no sense whatsoever. And so I thought I'd better point that out just so we can have some understanding of that problem. Yeah, because you look in the back of the book and it gives you an answer, and it's wrong. It's distressing. Also, the one that had you identify things as homogeneous mixtures, heterogeneous mixtures, and so on. For the salt, it said that it was a homogeneous mixture. And then it said that's because the salt isn't really pure. Well, the salt is 99.85% pure. And we went through a section that said nothing is perfectly pure. We have to have a certain tolerance. And so I would say, if they say salt, they mean pure within any tolerance, and then that would be, what would it be if salt is pure? A compound, right? So the compound would be the reasonable answer. You can at least defend the textbook's answer there that there are impurities in it, but then do you ever have anything that's a compound? You know, the textbook was clear in saying there's always going to be some impurities. You have to have a tolerance there. So a couple things there. One more thing before I continue with the lecture. Make sure your potential test questions are on things that I talk about in class. From the last class, there was a question that not only was not on something was on something I didn't talk about, it's on something that's not in the textbook that we're never going to talk about. So make sure that your potential test questions are on things we talk about in class. Okay, continuing on why carbon is special. Carbon atoms form bonds with other types of atoms readily so that we make lots of different interesting compounds with carbon atoms. So hydrocarbons are the most common thing we look at. Hydrocarbons, as you would have guessed, contain a hydrogen, hydro, and a carbon. Really not a stretch of the imagination to know that hydrocarbons means hydrogen-carbon compounds. What is confounding is that there are lots and lots and lots of compounds you can make with nothing but carbon and hydrogen. For instance, here are 3 different things. Each one has the same number of carbons and the same number of hydrogens. In this case, we call them isomers. Iso means same. I don't know, Mer. Honestly, I don't. But the isomers have the same chemical compound in terms of, or composition, I should have said, the same composition, but they're arranged differently. So when we learned our first naming rules, things like, well, if I take sodium and chlorine and put them together, I'm going to call it sodium chloride, unless there's, sodium and 1 chloride, there could be sodium and 2 chlorides, then I would say sodium monochloride. Well, now it gets a lot more complicated because you can have exactly the same atoms and have different actual chemicals, things that behave differently. And so you see we have different names. We have pentane. If it ends with ane, A-N-E, then it means you have all single bonds between the carbons. If it starts with pent is a prefix, like pentagon. What does pent mean? 5. So pentane means I have 5 carbons with single bonds. So all of these are pentanes because they all have 5 carbons with single bonds. So you see pentane, pentane, pentane. And then those prefixes, iso and neo, I'm actually not real clear on those. I think iso is saying that it's on the second carbon. And, chemistry can be confusing. I know physics can be confusing to some people too. But with chemistry, you have multiple names for the same compound. So for instance, we'll have coming up a slide that has 2-pentanol. And I looked and I said, yeah, it is 2-pentanol, but I'm sure that's also isopropyl alcohol or isopropanol. And so I went searching just to make sure I was right. And yeah, you have all these different names that are the same compound. There is a standard, the IUPAC, International Union of something chemistry, I think, has a naming method. And the naming method has you do things like, well, this here would just be pentane, and this would be 2-methylbutane, actually, because but means 4, and you have a methyl group on the second carbon in the chain. So there is a naming method. The textbook is really clear in saying, you know what? Don't sit down and memorize those things. If you were taking organic chemistry, which is a year-long class, yes, you would sit down and memorize those things. And you would have a test that would do nothing but have you name different compounds. But we're not in that class. We just want to have some basic understanding. So what's the point of this? The point of this slide is to understand that we have these isomers. Structural isomer, it's a different structure, but it's the same chemical compound. as far as the same chemical formula, I should have said, rather than compound. And you can see from the pictures, the geometry, the shapes are different. So then we have configurations. What does that mean? It means you can have the same isomer, but you can have different angles on it, different bends. And the different bends is going to make them behave differently. You guys, I mean, you know, we have things like, well, maybe you don't know. Protein folding stuff you can run on your computer when you're not using it for a screensaver. And what it does is it goes through and it calculates different ways you can fold a protein chain. The reason is if it folds into the right shape, it can interact with certain living cells. And so if you get the right shape, it'll do this. Wrong shape, it won't do anything, and it helps us define medicines and things like that. So the different ways of folding the same chemical isomer is an important thing. In our protein, we have these long chains of protein. You put them in the body and you put them in the right chemicals and they fold up into these little shapes. And those shapes are a big part of their function, how they work, which is astonishing to me. Our bodies are, to me, a miracle, which helps me believe more in God. So different ways you can arrange the atoms. If you have C5, if it's 5, what would you call it? It's going to start with pent. If it has 12 hydrogens, if you go through the math, that means you're going to have single bonds everywhere, and so that makes it an ane. So this is pentane. There are 3 different isomers, the ones we saw. If you go to the next one with 6 carbons, that's hexane. And there's 5 different isomers for hexane. And then I think the next one's heptane. I get, Yes, I get sept and hept confused, but I'm pretty sure it's heptane. Has 9. Octane has 18. 10. Decane? 75. 20. Dodecane. 366,319 different ways you could combine those. Well, that's why I'm a physicist. Oh, right. Those are representing 2 different structures. Now, if you look at those, based on what I've already told you, what can you interpret from those stick figures? Okay. Each one has 5 carbons. How do you know it's 5 carbons? Because you have to count the ends too. So 1, 2, 3, 4, 5. So there's our carbons.
Does that only happen with carbon?
If it's not carbon, you need to have the atom listed. So otherwise, you just have to guess. Oh, there's an atom and another atom and another atom. So it's only for carbon that they don't mark it, except for the hydrogens that if there's bond missing, you assume is hydrogen. So now that we have that, how many hydrogens do we have? How many hydrogens should we have on the end? 3. And all the rest are 2. And you might want, oops, that was supposed to be an H and I started putting another. You might wonder, I have the 2 H's on top and the 2 H's on bottom. That's really the way they are. Having those H's on top is why it's bent the way it is. So you can tell the way it's bent tells you where the H's are. So that's what it really means. Now, what's the difference between the one I've marked up and the other one? There's only one real difference. Okay, this one goes up and this one goes down to the left. What that means is this one here has the hydrogens on this side, whereas this one had the hydrogens on top. You put the hydrogens in a different place, the bond bends a different direction. And so even though these have exactly the same chemical formula and they're lined up in the same order, they're bent differently, and they're going to behave differently. Good to know, huh? So we call these conformations the different shapes for the same exact compound. I should have said of the same configuration. Too many C words. So the configuration is the order that the atoms are placed in the kinds of bonds. And then the conformation is then the shape, the physical shape it takes. Okay, first of our clicker questions. What's the chemical formula for the following structure? Jocelyn, Brandon, Raquel, and Brittany. Got channel 33, Raquel? Yeah. Okay, so we had 14 people all agreed that was C5H12. And this fine student here is not present. This fine student here, Tiffany, is going to explain to us how she came up with her answer. Oh, okay. Well, give us your reasoning still.
Well, I heard you say that every time there's a bend, there's a carbon.
Right?
I only counted 3 bends.
Okay. And that is a reasonable thing to say. Every time there's a bend, there's a carbon. So there's a carbon here, here, and here. But we also have to take the ends of the sticks, and we assume those are carbons as well. And so there's the other two. Right? So your answer, I can understand exactly where that comes from. It was a reasonable thought. But there's one more at each end. Okay, then how'd you come up with your number of hydrogens? I guess you didn't because it didn't give you different options for the same number of carbons. But for the hydrogens, you have to have a total of 4 bonds for each carbon unless they're doubles are 2. So you only had 1 bond in the end, so it had 3 hydrogens. You had 2 bonds and all the rest, so 2 hydrogens. So 3 plus 2 plus 2 plus 2 plus 3 gives us our 12. Any questions on that? Make sense? Could do it again on the test? Maybe, maybe not. We'll see. Fractioning. Fractioning is the term for separating these hydrocarbons. Let's say that you are in the oil business. You get this crude oil, and you want to take this crude oil and separate it so you can make gasoline. Now, this crude oil contains a lot of different hydrocarbons. It's not just one type of hydrocarbon. So you have to separate them, and that's what fractioning is. So you can see up there your basic fractioning setup. You have a furnace that heats up the oil. When you heat up the oil, just like water, when you heat up water, what happens?
It boils.
It boils and goes into a vapor phase. So they're doing that with the oil. They're heating up so it's vapor. Now, to me, that sounds scary, right? Because you have lots of things that are easy to light on fire, and they're volatile. They go into vapor nice and easily. That's what volatile means. So you have that crude oil vapor then that you put in what they call the fractioning tower. And the fractioning tower has different temperatures at different elevations. They control the temperature at different elevations. And so when you get to the point where you have reached the condensation temperature, the temperature where it will go from a vapor phase to a liquid phase, what temperature is that for water? 100 degrees Celsius. I didn't hear you anyway, so. 100 degrees Celsius. At 100 degrees Celsius, water will condense and form a liquid instead of being a gas. Well, for the different hydrocarbons, depending on the hydrocarbon, you'll have a different temperature where it will condense. And so you have different temperatures in that fractioning tower, and then you have condensation plates, and if condensation forms on them, it's collected and taken off, and depending on the temperature, it's a different kind of compound. So you can see the coldest temperature for condensation is what we call natural gas. It's still gas when they get it to room temperature. Then the next colder one is gasoline, and you go down to kerosene, diesel, lubricants. Lubricants means the oils we use. And then finally, tar is the sludge, the stuff that solidifies at a very high temperature. And so when you're refining the oil, the first step is to separate. So you have the stuff that's going to go into gasoline, stuff that's going to go to kerosene, diesel, and so on. So that's how they separate. It's kind of cool, right? Now they do a lot more chemistry on it after that. They'll probably throw in some additives and do things to purify it and get that octane level just right. How many people know the difference in saturated and unsaturated fats? Chips and popcorn tend to have. Is that good or bad? Okay. Now the fact is, I'm not sure which is good and which is bad. It's horrible to not know the difference, right? And I'm sure you can ask my wife, and she will tell you which one's better and which one's worse. But here's what we're talking about when we're talking about saturated versus unsaturated hydrocarbons. We're talking about the number of hydrogens that are attached to each carbon. If it's saturated, then it has the maximum number of carbons it could hold. If it's unsaturated, you could add more. So with a single carbon is called methane. You don't have an option of a double bond there. You have 4 carbons. If you go to something like butane, but is 4. I know, not quad or something like that. So you have 4 carbons. You have the saturated form, has no double bonds. Those are all single. The unsaturated has a double bond. But because of that double bond, there are 2 less hydrogens in the compound. So that's why it's unsaturated. It has less than the maximum number of hydrogens that you could put with those carbon atoms. Now, what can you tell me about the strength of a double bond compared to the strength of a single bond? It's stronger, right? So this is forming a stronger bond. And notice, because it has a double bond, instead of ane, that changed to an ene. So butane means they're all single bonds. Butene means you got a double bond there. And yeah, it gets worse. But that's the difference in saturated and unsaturated. So when somebody talks about saturated fat and an unsaturated fat, they're talking about the fats have chains of carbon in them. And if it's unsaturated, it has all of the possible hydrogens it could have. If it's unsaturated, it has some double bonds and less hydrogens. Okay, I already showed you this structure. So here is the picture that I tried to illustrate. You notice even the starting pictures now. It's taking the assumption that that because I have 6 corners, I have a carbon at each one of those corners. And then it shows the double bonds, and it shows 2 different versions. The arrow in between means it just goes back and forth between them. You can have both. And so we draw those shifting bonds with the circle inside. There's actually another way of drawing it with dashed lines, but we're going to go with the circle because it's easier. So this here is called a benzene ring. Benzene, good or bad? Benzene. Generally bad. When you're working in research, you get research grade ethanol. Research grade ethanol is like 100% ethanol. But notice I said like, and it's not just because I'm from California. It's because it's not perfectly pure. In trying to purify it, they put in chemicals to collect impurities and take them away. But that introduces what chemical they use? Benzene. They put benzene in there to try to take away the impurities to make it closer to pure. So we get this alcohol that's 100% ethanol. Ethanol is the alcohol that bad people drink. Supporting our stance here at Union College.
I wouldn't call them bad people.
Right.
No, I wouldn't call them bad people either if I was being
They just make
serious
poor
and not
choices.
joking. Well,
Anyway.
yes, anyway. But ethanol is the kind of alcohol that people drink. And so some of the students were like, we're having a party. It costs so much to buy liquor. Why does it cost so much to buy liquor? Because you're paying a huge tax on it.
Because,
And here in the lab, they get this 100% ethanol really cheap because it's not expensive to make ethanol. And you don't have to pay a liquor tax on it because you sign off saying it's going to be used for lab work. So they grabbed some of those bottles and took them to a party and they drank those.
oh, my God.
Is this real life?
Yeah, these are
Here?
no. Washington State University. Don't do this.
Okay.
And the next day they had wicked hangovers because that benzene ain't good for you. And so they polluted themselves a little more literally than we usually mean when we say they got polluted at the party. So benzene is not something you want to eat, drink, or otherwise. But all it is an organic compound. It's a ring of carbons, basically. So here are some special cases where you start with benzene and you do something special with it. So you have toluene. Certainly you know about toluene. You probably don't know it, but you do. Because, we're TNT, dynamite. You guys know that song, right? No. You young kids. So TNT is the chemical that makes dynamite go boom.
Boom.
Dynamite is what Alfred Nobel made his money on. That's what funds the Nobel Prizes, is the invention of dynamite, which is using essentially, I think it's limestone, to stabilize the TNT so it doesn't go boom without you wanting it to go boom. So TNT stands for trinitrotoluene. So trinitrotoluene is a benzene ring that, if I remember right, just has 3 nitrogens sticking off of it. I think that's the way it works. I didn't look it up before class. And it's very unstable because nitrogen is unstable. Naphthalene. Where do you find naphthalene? Daily life. No? Mothballs. Mothballs, very odoriferous. They have a strong smell that apparently moths don't like. That makes us, think of grandma's linen closet. And then dichlorobenzene. I used that as a solvent in graduate school, but I couldn't tell you anything else about it. Okay, let's go for another question. What is the chemical formula for this structure? You notice it's not identical to the last one. And this time you have different options for both the C and the H. And while you're doing this, I'll sing the old jingle. C and H from Hawaii. Pure cane sugar. That's the one.
My school is next to a C&H sugar factory. It smells terrible.
Oh. This time it got you. Keep choosing that person, not here.
Are we going over this last on Monday?
We'll be reviewing for it, not going over it, but we'll go over it after we've taken it. Okay, still waiting on Skyla, Jocelyn, Jackie, Larissa. Now just waiting on Jocelyn. All right. We had a majority there. Jackie, tell us what your thoughts are on this.
Okay, so I said C, but so because I was a little confused about the double bond, but it doesn't count as a heart rate, does it?
Nope.
Okay, so then it would probably be A. Right? Because there's 1, 2, 3, 4, 5, and then 1, 2, 3, 1, 2, 3, 1, 2, and then you have the double bond.
So let's just go through this sequentially. So how many hydrogens do I have on the top carbon? 3. I was going to just put red lines, but if I just put red line, it looks like I'm ending in another car or blue lines. How many do I have on the next one? Just one. Just one, because it has 2 bonds going one way and 1 going the other. So it already has a total of 3 bonds. So just 1. How about the next one? Same reason. And the next one? Where should I put those 2? Yeah, both on top. And the last one. And now we can add them up. 3, 6, 7, 8, 9, 10. And so, Jackie, realizing her situation, corrected to the right answer. Any questions about how that worked? We're learning things, right? I mean, that's my only goal here. Okay, heteroatom. What does the word hetero mean? Different. So when we're talking about hydrocarbons and organic compounds, heteroatoms are atoms that aren't hydrogen or carbon. So anything else would be a heteroatom. And then functional groups are different combinations that show up all over the place in organic chemistry. So here is a list of the functional groups. Now, once again, just reiterating what I said earlier on, the textbook is very clear. Don't spend your time trying to memorize all this stuff. Try to learn general ideas. So on your potential test questions, try not to give something that's specific, like, well, what is the name of, this compound, right? Because I'm not encouraging you to spend time memorizing that kind of stuff. So I don't expect you to say, oh, a phenol looks like this, right? It's more of understanding that they exist and what a functional group is. So here's our functional groups. Now, the picture on the left, they all have 2 carbons. 2 carbons is F. Single bond means it's ane. So all of these are ethane, ethyl, and then amine. The ethyl is because of the continuation part. So ethane is just simple. Ethanol has an additional functional group. The alcohol is defined by having a functional group of an OH attached to the carbon. So alcohols always have this thing here that's called a hydroxyl group. OH is hydroxide, so it's a OH bonded to a carbon is the hydroxyl group. So this is ethanol. This is the stuff that people drink. When they say, yeah, there was alcohol, that's what it is. And then ethylamine, that has an amine group. So here's the amine. Now remember I said that our proteins are made of amino acids. The amino acids have amine groups and are acidic. So an amine group is a nitrogen attached to the carbon, and then it could have different variations on it. So here are, not is, other common ones, phenols. It has the all from alcohol, but a phenyl group, The phenyl group is the ring of 6 carbons. So the phenolic group is the 6 carbons in a ring with an alcohol, an OH, on it. Ethers have an oxygen between carbons. How many bonds should oxygen form? 2. And so here it has 1 to one carbon, 1 to another carbon. That's what makes an ether group. Ethers, ether used to be used to knock people out in surgery, right? The textbook talks about that. So there's some issues with ethers of safety. Other groups here, ketones. You ever heard of ketoacidosis? Well, people who are like on the, I can't remember the dude's name now, that diet where you only eat like meat and don't eat carbs. Yeah, Atkins diet. One of the things they actually want to reach is ketoacidosis, where your body doesn't have enough sugar and it's producing ketones, which makes your breath have this fruity smell because of the ketones. It's really not good for you, but that's one of their goals. Just as a note on health, you need sugar to operate. You need carbohydrates to operate because that's what is the fuel for your brain. And so, at least according to my sister, one of her relatives went on the Atkins diet, and you could actually see a diminishing in brain capacity. The person used to win almost every game they played, really good at games, and then went on the Atkins diet, lost almost every game. Just couldn't think as clearly because you need the sugar for your brain to work. So keep that in mind when it's like the night before the test. You want to make sure you get your exercise, get some sleep, get up in the morning, have a healthy breakfast with complex carbohydrates. Complex carbohydrates are the ones that take longer for the body to metabolize, so you don't have a sugar spike and you'll have sugar throughout the day to keep your brain operating functionally. Okay, a couple other ones. Esters, polyester. Carboxylic acids, you have a carbon double bonded to an O, then single bonded to an OH. Those are really strong acids. Amides, notice amide versus amine. They both have the nitrogen at the end, but the amide, you have an oxygen double bonded to the carbon that the nitrogen is bonded to. And finally, aldehydes, like formaldehyde. So now just some quick pictures here before we go. Alcohols, the boiling temperature. We've talked about boiling temperature. We had a question homework about boiling temperature. And you have different boiling temperatures for methanol versus ethanol versus isopropyl alcohol or 2-propanol. Why would those be different boiling temperatures? Why does propanol have the highest boiling temperature and methanol the lowest boiling temperature? No. I believe as a general rule, the more carbons you have, the more it can stick together, the less likely it is to go into vapor. On the alcohol, something that the textbook mentions, I know I spoke ill of people who drink alcohol already, but there's some things that really are useful to know. When people measure the alcohol in a drink, what do they say? It's blank blank, like
5%.
Okay, 5% they rarely say. That would be an accurate thing, and that's what I want us to be able to translate to. They label it in proofs, but proof is merely twice the percentage. So something that's 100 proof means it's 50% alcohol. If it's 100% alcohol, what would its proof be? 200. And so things like Everclear, which I've never even seen, are supposed to be really close to that 200 proof, close to 100% alcohol. And this, that'll end you. This, that'll end you. So that's, you want to make sure you drink no methanol, no propanol. Don't be like, I got to have some alcohol. I'm going to go buy some rubbing alcohol. it'll end you. It's bad. At least the ethanol, you have a chance of surviving, right? As long as you don't make a bad decision or drink too much. Do you guys see that dude? Was it Puerto Rico? I think it was in Puerto Rico. He was in a bar and these guys were taking bets on how much tequila they could drink. And so he said, "Hey, can I get on this?" Yeah. So he puts in his money. He drank a whole bottle of tequila. Yeah. He died like 5 minutes later. Because alcohol will kill you. Okay. Have a great weekend and don't kill yourself.